P5, let me get myself a pen. So you'll be able to hopefully see most of what I'm doing in the classroom and at home. And P5 is on the electromagnetic spectrum. Now I'm just going to throw out a few things quickly that we need to make sure we cover. We need to look at color. Okay, we're going to actually look at the electromagnetic spectrum. We need to know about using long wavelengths. Sorry, I know I'm writing fast, so it gets a bit messy. Using short. So the only difference between these two, long and short wavelengths. I'm going to talk quickly about the black car versus a white car. And we'll have a quick look over refraction again. Now refraction does come up in P4. And it's obviously covered in P5 because we're looking at parts of the electromagnetic spectrum that refract, which is all of them, because they're all got what in common. What are they all? Anyone in the classroom? What's everything in the electromagnetic spectrum? It can be if you can see it. Can you see everything in the electromagnetic spectrum? No. Right. So what they all got in common then? They're all types of. They are all types of waves, but only one type of wave. Anyone know what type of waves they are? It's two types of waves. I know you haven't watched the P4 video yet. We had longitudinal and transverse waves. Which waves are we talking about here? Be brave. Which one?
Transverse.
Transverse, spot on.
Yeah.
Yes. Trust the girls to all get it right, the boys to jump in when they think they got it right. I like that. Transverse waves. What are longitudinal waves? Let's cover that off while we're here. What's the one that we always talk about in GCSE physics? I'm doing it right now. Sound. Okay, but we're not talking about sound. This has got nothing to do with sound. Common misconception: ultrasound. It's medical imaging, so it must be part of this. No, it's sound. So it's not part of the electromagnetic spectrum at all. All the electromagnetic spectrum means, and we do this more A level, is that we look at the electric fields. And we look at the magnetic fields, and when they come together, you end up with an electromagnetic wave. That's the only thing you need to know about where the name comes from. So in terms of how that affects us in GCSE, we just need to know some of these key points and what they're really standing for. So who's going to get me off with, how about we draw the electromagnetic spectrum just very quickly.
Yeah.
Now, I have offered you up this before, that if you made a nice one, you could cut it out of your book and stick it on your revision notes. That's a good shout. Or you could find one online. Don't draw one with me now. I would find a good one, stick it on your revision notes. It's so complex to draw that you don't get any value out of it. This is one of the few times I would suggest that. But I'll scribble one on the side anyway, because we're going to work our way through it. So let's start with really short waves. Sorry, really long waves, and let's get up to really high waves. You can see why I don't recommend you draw this. That's terrible, but you get the idea. So these really long waves down the end, what are we talking about? So we asked you to learn a mnemonic a long time ago. Radio waves. We listened to them in the car. Radio waves. I'm just going to put the letters there because we're going to end up with a mnemonic. That's probably more important here at this stage. It's what gets added to this diagram that's more important. Radio waves, what comes after R? Your phones use lots of them. Somebody said it. Microwaves. Okay, so we've got RM. Microwaves. What makes us hot? What kind of waves reach us from the sun that make us hot? They are heat waves, but the proper type of wave is? You are right, just give them a chance to get it right. Starts with an I. You can't see it. No, it's all right. Go on, give it to Jim. Infrared. Okay. It's all right. Here's the easy one that everyone always forgets. Why do they forget it? Because they can see it. Visible light. Okay. What comes after visible light? Which is the one that gives you skin cancer? Girls, you've got. Oh, I've been really sexist there. Really sorry. Anybody is allowed to wear makeup. On your makeup, it'll have a protection from these kind of rays.
Ultraviolet.
Ultraviolets. Good save there, thank you very much. After ultraviolet, we start getting into a medical imaging one. The one that everyone can remember, X-rays, good.
And then is it gamma rays?
It is in fact gamma rays.
So they're the ones that like kill cancer cells.
Right, well, they can be used to do that.
Oh.
Okay, they can also be the ones that cause cancer cells.
Oh.
They're a double-edged sword. Okay, so if you're exposed to gamma rays now in a non-medical environment, you would say it's bad, but in a medical environment, they can be used for medical intervention. Absolutely, they can be used to kill cells. You just got to make sure you kill the right ones because they kill everything. Okay, so the reason I've written that mnemonic up there like that is because the diagram isn't that important to us right now. We just need to know that we have radio, microwave, infrared, visible, UV, X-ray, gamma. And there's cosmic after that, but you don't need to know that GCSE. Okay, these are our wave types of the electromagnetic spectrum. They all have a purpose. They can all be applied. We can use them for lots of goodness. We can use them for badness as well. Okay, this is a part of physics, guys, where you have to have a little bit of understanding, a little bit of knowledge, but need to know how to use it. So if I said to you, I want a type of wave that can travel a long way but go through things, what kind of waves do we know about? Where if I had a stereo in here, what kind of waves would it be listening to? FM, which is what type of wave? Radio wave. Do the walls matter to FM? No, because it's a really long wave. And if you could see a radio wave, it would fill this room up, one end of it to the other. Okay, really long wavelength. Microwaves, they're all around us right now. Your phones are pinging out microwaves left, right, and center. That white box up on the wall there. Anyone know what that is? It's Wi-Fi router. What's Wi-Fi? Anyone? Wi-Fi? It's not PS5. What's the Wi-Fi? It is a part of the electromagnetic spectrum. Anyone know what part of the EMS it is?
Microwave.
It is a microwave.
Yes.
In fact, it's almost exactly the same frequency that's used in your microwave ovens to cook food. You can't cook anything with that, by the way. The energy's too low. Okay, so Wi-Fi doesn't go very far, but the energy in a microwave oven is able to vibrate fat and water cells, particles in food. That's why they heat up. Right? It's just transferring energy around. We look at infrared. We're pretty obvious. We sit in the windowsill, we get quite warm, don't we?
Yeah.
From the sun. Yeah, we use infrared in medical a lot. Anyone seen what happens with premature babies? Where do they put them in, please? An incubator, absolutely. What's the incubator got all the way around it? Infrared. Okay, very expensive incubators. About £80,000 we raised for one that we got for a maternity ward because it's quite important you don't cook the premature baby. Okay, so heat control is very, very important. And I make that joke, and I do apologise if anyone is offended by it, but it's meant to be humorous. Obviously, I don't like to cook babies. Visible light. What do we understand about visible light, guys? We can see it. Yep, that's the obvious parts, but it breaks into what? How about, because I've intentionally drawn it down here, let's add visible light up here. Okay, and we have two numbers that we need to know. Who's going to tell me that they can remember the two numbers that I told you that you had to remember? Is it 400 and 700?
I don't know.
Anyone? Oh. Should we know that it's 400 and 700?
Yes. Yeah.
Yes, well done. It is 400 and 700. I didn't get to drink my coffee. Right, so we got 400. So please write this in. 400 and 700. And these are nanometers. Little n, little m. nm. For nanometers, they're very small. You can't see a wavelength of light. It's too small for your eyes. Okay, but you can see colour. Right, shorter wavelengths. I probably should have drawn this the other way around, 700 and 400, but hey, let me off the hook here. I've probably drawn it back to front, but it won't matter too much for our purposes here. Our very short wavelengths are our blues. Anyone want to tell me what might be the other end?
Red.
Reds, absolutely. Now, the reason why I said I've drawn it kind of back to front is because our reds actually go this way, down the electromagnetic spectrum. Our blues actually go this way. So I might have drawn it in a slightly confusing way, but all you need to know for visible light, guys, is we've got 400 nanometers and our blues, that's 700 nanometers and our reds. What's in between?
Purples.
Yeah, there would be purples. What else? Yellows, yeah. What's an easier answer to this? Every other colour. They all belong in there. Yep. So, yellows, greens, purples. Yes, you can have them all. They're all in there. What if I put all of them together and send them to to your eyes at the same time? What would you see?
Visible light.
You would see. You wouldn't say I can see visible light. You would say I see
Light.
what kind of light?
White.
You're all right, by the way. White light. Yeah. They're all saying it. You're just saying light. You need to be more descriptive. White light.
Yeah.
So white light isn't actually a colour. White light is a combination of all the other colours. Now, please don't get mistaken here on black light. Okay, black light doesn't exist. No, that's rubbish. If you can see it, it is a colour of light is reaching you. Okay, when we say blackness is no colour, what they're saying is it's an absence of light, and you can absorb so much light that it appears black. An example of that would be in our universe. Anyone know what I'm fishing for? Space, but what's in space that absorbs all the light?
Black hole.
Black holes. Okay? And space is a good example too, absence of light. Black hole, same thing. Okay, so that's all we really need to take away from colour and electromagnetic spectrum. Right, let's use some of these long wavelengths. So we're really talking about R, M, and I for long wavelengths. Radio, we've already had FM. We've had Wi-Fi for microwaves. Infrared, we've had incubator. Okay, they're all, you do need to know examples. What else can I use microwave for? We've talked about communication.
Cooking.
Cooking, yeah, absolutely. Infrared,
Warming up.
yeah, heating as well. Incubators, heating. Radio waves, can we use them for cooking?
No.
Probably not. Okay, we need a frequency that will vibrate the water and fat particles. So it won't be high enough to do that. Not, that being said, I wouldn't want to walk in front of a radio transmitter. There's quite a lot of energy that comes out of them. So it's mostly communication. So our short wavelengths. Now our short wavelengths, we do typically include visible, ultraviolet. Oh, I didn't spread them out. Ultraviolet, X-rays, and gamma. What do we use visible light for? Seeing, yeah, that's probably the obvious one. Is there anything else we can use it for? Okay. What about if I had a secret signal set up that if I flashed my torch at you 3 times it meant run?
Morse code.
What colour was that torch light?
White.
Let's say now it's red. I'll send you a red one. 3 flashes mean run.
Yeah.
What could I do if I changed it to blue? And it had 3 flashes, something for blue. So if I use visible light, I can use it for communication as well. Okay. We do that without really realising we're doing it. Okay, ultraviolet. Now this one catches people out a little bit because we always think of badness. But what can we use ultraviolet for? Speak up. Oh yeah, gel coats. If you don't know what gel coats are, what goes on your nails can then be set using ultraviolet light. So it won't set in normal light, but it will set under ultraviolet light. Okay, not had that one before. What else can we use UV for?
Oh.
Is it good for your skin?
No.
What is it? Yeah, is tanning good or bad? I know, it's a double-edged sword, this one. In a medical sense, is tanning good?
No.
No, they're all shaking their heads just in case you can't tell at home. No, it's bad. So what's it actually doing to your skin cells? Give me 2 seconds.
It's like cooking them.
It's not cooking them,
Burning them.
not burning, but you're on the right track. Is it making them healthier or killing them?
Killing them.
It's destroying them. Yeah. In fact, that's what's happening is when you're tanning, you're releasing the melanoma in your skin cells. You think of it as a lovely tan. In fact, what you're doing is killing lots of skin cells. How can that possibly be good for you? Since the person doesn't tan, of course. So if they could kill your skin cells, is there any limitation of what else they might kill?
No.
Give me an example when we want to kill something.
Cancer cells.
Yes, but okay, now think something a little bit more current. Hey, what might UV light do to coronavirus?
Kill it.
Well, okay, it's technically not alive, so it can't be killed, but it could destroy the cells that make up the virus. Yep. So we can use UV for, and I'll squeeze it in here because I put gel coats far too large. We can use it for, anyone know what the word is I'm fishing for? Starts with an S. Sterilize. Well done. Okay. And I'll squeeze it in here. Sterilization. Sterilizing. Yep. Very important, guys. You don't always think of these as being good or bad. They can be every context. X-rays. This is possibly the easiest one on the board. What do we use it? X-rays for?
To see your bones.
Medical imaging. Yes, bones is fine. You would get the mark for that. I'll put medical imaging because it's a better idea to use the proper term. There are other things we use X-rays for, but generically medical imaging is pretty good. Gamma. We've already had a few people mention uses for gamma. Who had the gamma one? Yeah, go on then. Yeah, killing cancer cells. So what I'll try and do, go on.
Isn't it also for like MRI scans?
Magnetic resonance imaging.
So
No.
Oh, okay.
Think of it as like a giant magnetic field.
Okay.
It is part of medical imaging, absolutely. And it would be part of the electromagnetic spectrum, because if you have a magnetic field, you induce an electric field. So there is electromagnetics there, but not to be confused with an X-ray or a gamma ray.
Yeah.
So we don't treat it as a separate entity on the EMS. Okay, so I'm going to draw a little picture for you. I'll sneak it wherever I've got a bit of space here. And this is a person's head. I know, it's amazing, isn't it, my drawing ability? And we're going to have a little gamma ray source here, and it's going to pass. Now the thing with gamma you've got to realise is that we've probably passed all the way through. Okay, all right, so, and it's going to damage everything it comes in contact with. It's got lots of energy and it's going to start damaging cells, so we want to limit the amount. So what we do, instead of having just one and shooting at the cancer cells until we get lucky, is we typically will have quite a few of these. Okay, and you're start to get the idea as I draw a few more that they are all doing something. What are they all doing? Going through where? One point. Now, one of the reasons why, if you've met someone who's had radiotherapy, not to be confused with chemotherapy. What's the word chemo stand for? Chemicals. That's chemistry. Okay, chemotherapy, and this is radiotherapy. So if you meet someone who's had radiotherapy, a couple of things, it does tend to kill hair cells. Okay, it's pretty nasty. It's not good for you. Short term, can be good for you long term. It will kill hair cells, so they do tend to lose their hair. But there are ways and forms of radiotherapy where people don't. So there's ongoing developments there. But what the best thing about radiotherapy is it's so precise that if the tumor is accurately mapped, if they know exactly where it is, they can make sure all these beams pass and meet at that point. Okay, and then they just move it out in order to catch all of the tumor. It's not perfect, but it's pretty effective. To know where all of those are pointing, because you don't have it go in one go, you have multiple sessions. You'll often see they have little marks on them. They're little tattoos. They're just like little pinprick marks on their heads in various places. It's to make sure between every session that the gamma rays are lined up perfectly. Okay, so I've just saved you asking them why they have dots on their head. Okay, which would probably be a discussion point they don't want to have. But it's amazing. If we went back 40, 50 years, the idea of doing this would never, medical wise. So we've made huge inroads in how to treat, because otherwise you'd have to surgically remove it. And if you can imagine trying to get into the middle of someone's brain, it's a bit of a non-starter. Okay, so this is a good example where physics is helping medical sciences. Right, that's radiotherapy. That's using gamma rays. During class we put in lots of other examples there, so we'll leave that for the moment. Anything extra added on there. You should have at least a couple examples for each one. Okay, so that you've got something in your back of your mind going, if they ask me about radio waves, I'm going to talk about this. If they ask me about X-rays, I'm going to talk about this. So if they give you a 6-mark answer question, you look like you know what you're talking about because you're using proper examples. Okay, you don't need to write loads and loads about something that they're not asking, but it shows that you know what you're talking about. It might be the difference between a 5 becoming a 6. Okay?
Yeah.
And we like that. Tell me about a black car versus a white car. Why did I put that on the board? Go. Okay, so let's chuck that word on there. Absorb. So which one's hotter? Black one. So what would you feel when you touch a hot car? Heat. That's energy, right?
Yeah.
The energies come from the black car into your hand. So it's absorbing energy, isn't it? It's not giving energy away. Doing both. So if it's absorbing more, it must be also, what's the word I'm fishing for? Emitting. Okay, so make sure you got emitting down. Yeah, go for it.
How come is it that black absorbs like more heat than other colours?
Okay, so in the very simple terms to this is that infrared is color based. So what we deal with, let me start the other way around. I'm holding up a piece of paper for those people at home and it's white. What are you seeing right now?
Oh, white.
White. What are you actually seeing? Color. No, forget the piece of paper. You're seeing white, but what's white made up of? I know, it gets confusing when I do this. What's white made up of? We just did it before.
What do you mean?
So white is made up of everything. So I'll even add this in for you. Everything
Colour.
is white. So at the moment, what's bouncing off this piece of paper?
Every colour.
Everything. Okay?
Yeah.
Because white is made up of all the colours. So if I had a black piece of paper, what's not happening?
Not all the colours that are coming off there.
They're not reflecting.
Yeah.
So if they're not reflecting, where's the energy going?
Into the...
It's being absorbed. And now, the reality is that actually quite a lot of the light is being reflected off a black vehicle, but a lot less than a white vehicle. So we're keeping this as a relative thing. We're trying to make this a practical application of, everything right?
Yeah.
Cool. We're trying to make this a practical application of what you'd find in the real world. And most people, I don't have to teach them physics to ask them which kind of car will get hotter in the sun, black car or white car. 99% of people without any physics wouldn't be able to tell me the black car gets hotter. The question is, can you tell me why? And the reason is the black car is absorbing more because a white car would reflect more. Now, which one's hotter first thing in the morning before the sun comes up? You go around the car park, you can get in trouble for touching everyone's cars. Which one's hotter?
The black ones.
Is it?
The white one.
Well, you had a 50-50 guess, so you've rattled through both of them. Anyone want to have a guess why the black one might be colder?
Oh.
Go on, you've guessed everything else. Why not have a go at this one?
Is it because it absorbs like the cold energy as well? So,
Well, you're on the right track. I don't think we call it cold energy.
well, the heat energy. But it's not,
Yeah,
it's
okay,
not
alright.
hotter than the other cars.
Okay, so first thing in the morning, what's that black car trying to do? It's trying to absorb, right? What happens when you touch it and you're hotter than the car is? What's it doing to you? It's absorbing your heat. So it feels to you cold. What's it doing when it feels hot? It's emitting the heat to you. So the only difference is you. Okay, and what temperature is that? Okay, so if I give you an infrared thermometer and send you out first thing in the morning, you're going to measure lots and lots of things and tell me that they're probably really cold. A metal pole or a telegraph pole is a classic one. Do that at 8 o'clock in the morning, you'll come back and tell me it's really, really cold. Go back and do it 2 o'clock in the afternoon, you tell me it's really, really hot. Okay, it's because During the morning, it's going to be absorbing until it gets to a point where it starts emitting the same amounts as absorbing. It gets to a point where it's at the same temperature. So if we put a black car out in the car park, it'll get hot. It'll keep getting hot, and then it'll get to a point where it's emitting the same as it's absorbing. It'll get to a point where it won't get any hotter. And it's got nothing to do with temperature. It is all about emitting and absorbing energy. When you've got a certain amount of energy, you are at a certain temperature. I could do the same thing to a table in this room. We won't do it because it's pointless. But you get the idea of black car, white car. But the two key words you must use, absorb and emitting. And please make sure you are talking about energy. Okay? Right, refraction. I said we'd fly through this one. We're doing pretty good so far. So refraction. What do we need to know about refraction? What is it to start with? Not reflection, refraction. Anyone got diamond earrings on? What does diamond earrings do if I hold them up in the sun? Keep it simple. Take it out of physics for a second. What would a non-physics person say about diamond earrings in the sun?
It will shine.
Shine. Okay, better than that?
Oh,
In like the diamond, it shows like a rainbow.
Rainbows, yeah, good. Rainbow, what else? Okay, I was going for sparkly, okay, but rainbow is probably better than sparkly. A physics person would say refraction is occurring. The light is going into that diamond and it's doing something inside the diamond before it comes back out. Different wavelengths of light do different things. Okay, so inside our, we'll go back to the glass block. Now this is in P4 anyway, so you're going to have seen this twice now if you watch both videos. So if I have my glass block and I've got my light, and that's meant to be a straight line, and this is my, anyone know what this is called? Normal, good. Couldn't get that out of the last class. Normal, okay, when it reaches the, I've lost my words now. So my angle of incidence here, when it reaches the face of the glass block, it's going to bend towards the normal. And then when it leaves, it will go back to the same path. Not the same path, parallel to the same path would be a better way of describing it. Parallel. Okay, so in this instance, we've got light bending towards the normal because it's going from a less dense to a more dense. I'm not going to rattle on too much about that now because it's in the P4 video. We went into quite a bit of detail about it. Please make sure you look that up. This is electromagnetic spectrum. These are light waves. Sound waves do something different. In fact, it's almost completely opposite. Don't worry about it. All right, just turn it off later. Okay. Any questions about that? Because if you're thinking it, someone at home might be thinking it. We have rattled through it very, very quickly, but I want to get on to a bit of P3 energy. All good? Okay. Right.